Hi all, in today's session we are going to study about the various losses of transformer and efficiency of transformer. The various losses which are present in the transformer are actually the core loss and copper loss. This core loss is further classified into two, that is hysteresis loss and eddy current loss. The relation for hysteresis loss and eddy current loss is actually given here. This hysteresis loss is actually occurring due to the magnetic flux reversal, and this eddy current loss is occurring due to the eddy current. In this relation, this nu is actually indicating a coefficient known as Steinmann's coefficient. Bmax is actually the maximum value of flux density, F is indicating the frequency of flux reversal, and V is representing the supply voltage. Similarly, in this relation also, P is indicating a constant. Bmax is actually the maximum value of flux density, F is frequency, and T is actually the thickness of lamination. Both these losses, that is hysteresis loss and eddy current loss, can be reduced by providing a laminated structure for the core, and it is made up of steel with high silicon content. That is mentioned here. As we have seen in our last video session, the transformer under no load condition will be taking the power from the supply in order to compensate the core losses only. You will get a clear idea about this point when we are studying about OC and SC test in the next video session. Now you just need to know that transformer losses are of two types, there is core loss and copper loss. This core loss is actually further classified into two, there is hysteresis loss and eddy current loss, and their relations are given here. Both these losses can be reduced by providing laminated structure and by making the construction of core with steel of high silicon content in them. Next is copper loss. Copper loss is actually the losses which are occurring in the resistance of the windings. We have also studied this in our last video session, and we have also solved the problems associated with them. From the relation of copper loss, it's very clear that copper loss is actually directly proportional to current square. It can be also said to be that the total copper loss is actually directly proportional to kVA square, because in the power rating of transformer, it is actually in kVA. The reason for that also will be explained in the next video session. So if you are seeing here, the total copper loss is actually directly proportional to current square. So we can say that total copper loss is directly proportional to kVA square because the voltage of the transformer remains constant. So under half load condition means the current will be reduced to half. If it is 1/4 load condition means from the power rating is actually voltage into ampere. That is voltage into current. That's why it is having the power rating of kVA. Since the voltage is remaining a constant one, if a transformer is said to be in full load condition, the current which will be flowing through the transformer will be the rated current. If the transformer is said to be in half load condition, then the current which will be flowing through the transformer will be half the current, keeping the voltage a constant one. Since the copper loss is directly proportional to current square, we can easily say that copper loss is directly proportional to kVA square. The square is only for the term current. So if we are seeing here copper loss at half the full load means the current will be half of the rated current. Since the copper loss is directly proportional to I square, the copper loss at half full load will be actually 1/4 of the total loss which is occurring at the full load condition. Comparing with the rotating devices, transformers are comparatively highly efficient piece of equipment. This is because the friction windage losses won't occur in the case of transformer because there are no moving parts in them. The only losses which are occurring in the transformer is core loss and copper loss. The standard relation for efficiency, you are quite familiar with this. Output divided by input. Input can be written as output plus losses. The losses which are coming here is actually the sum of copper loss and iron loss. We can write the efficiency as input minus losses, which is actually the output. So these two terms, if you are dividing, it becomes 1 minus losses by input. Next we are going to obtain the condition for maximum efficiency. This is actually a very important topic. From the primary equivalent circuit, we can say the copper loss is I1 square R01. From the secondary equivalent, we can say it as I2 square R02. In the last video session, we have solved a problem and we have proved that these values are one and the same. And the total iron loss is actually the sum of hysteresis loss and eddy current loss. Together it can be written as Wi. From this equivalent circuit, I can say that the input power which is being given to the transformer is V1 I1 cos phi 1 that is actually the power rating in the case of AC, that is Vi cos phi. So the input power which is being fed to the transformer is V1 I1 cos phi 1. Similarly, the power which is being available at the load can be written as V2 I2 cos phi 2, where phi 1 is actually the angle between V1 and I1 and phi 2 is actually the angle between V2 and I2. Those angles we have seen in the vector diagrams of transformer for different load conditions. You may refer that video session. Since the input power to the transformer is V1 I1 cos phi 1, we can write it as the primary input because the input will be provided to the primary side. So we can say the primary input as V1 I1 cos phi 1. From the previous slide, we know that efficiency is equal to input minus losses by input. So the same relation can be used here. Instead of input, we will be writing V1 I1 cos phi 1 minus losses divided by V1 I1 cos phi 1. We will be writing, or we will be substituting the values of losses here. Then further simplifying it, we will be getting the relation like this. In order to obtain the condition for the maximum efficiency, you have to differentiate this efficiency term, that is you have to find the first derivative of it and you have to equate it to 0. From there you will be able to obtain the condition for maximum efficiency. So while taking the first derivative of this term with respect to current, we are taking the derivative with respect to current because the current is the only variable component here. All others are constant terms. So we will be differentiating this equation with respect to current. We will be getting the term like this. Then further equating it to 0 in order to obtain the condition for maximum efficiency, we will be getting the relation like this. While simplifying this relation further, that is this cos phi 1 terms gets cancelled, V1 gets cancelled, we will be able to obtain the relation as Wi is equal to I1 square into R01. So this is actually the condition for maximum efficiency, that is the value of copper loss will be same as that of the value of iron loss. As we all know that the iron loss remains to be a constant one, the only method by which the maximum efficiency can be achieved is by making the copper loss value same as that of the iron loss. As we have obtained the condition for maximum efficiency as the value of copper loss is same as that of the value of iron loss. Now from the relation of efficiency, that is output divided by output plus losses, this output power can be written as V2 I2 cos phi, and this losses is actually copper loss plus iron loss. But under the condition of maximum efficiency, these two values are one and the same. So we can write the relation as output power V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus 2 times Pi, because the value of copper loss is same as that of the value of iron loss under the condition of maximum efficiency. Next we are going to see what will be the power rating of the transformer under this maximum efficiency condition. That is the output kVA, that is actually the power rating of transformer corresponding to the maximum efficiency condition. As I said before, the power rating of transformer is always said to be in kVA. It's not in kilowatts. The reason behind that will be explained in the next video session. Now you just need to know that the power rating of the transformer is always said to be in kVA. Power rating of the transformer as well as generator. AC generator is always said to be in kVA. Regarding AC generator, you will be studying about it in detail in the synchronous generator video sessions. Now we are studying about transformer, so you just need to keep in mind that the power rating of the transformer is always said to be in kVA. So now we have to find at which kVA value this maximum efficiency condition can be obtained. That is what we are going to find next. Suppose at some fraction of the full load kVA, that is some fraction of the rated kVA, let that fraction be x. At some fraction x of the rated kVA, if the maximum efficiency condition is occurring, from that particular fraction of the kVA value, we know that its voltage rating term remains the same. That fraction is reflecting only on the current term. As we know that the copper loss is actually directly proportional to I square, and if PC is actually indicating as the copper loss under rated condition, then at some fraction of the rated kVA, the copper loss can be written as x square into PC. It has been explained here very clearly. Suppose the maximum efficiency condition is occurring at say 3 by 4th of the full load kVA, or else I will be giving you another example. If suppose the transformer rated kVA is 100 kVA and its maximum efficiency condition is occurring at 75% of the full load condition, that is 3 by 4th of the full load condition, that is 75 kVA, and if the copper loss at full load kVA, that is 100 kVA, is 10 watts, then the copper loss which will be occurring at 75% of the full load kVA will be 75 by 100 the whole square into 10 watts. That same thing is written here in terms of X fraction, and the total copper loss here is considered as PC, and the iron loss is PA. So at this particular fraction of the full load kVA, the maximum efficiency condition is occurring, means these two terms will be equal. So now for maximum efficiency condition you have to equate these two terms, then you will be getting the value of that particular fraction X as square root of PI by PC. So you can find the kVA corresponding to maximum efficiency condition as X times that of the full load kVA. Full load kVA will be given in the problem. You have to find the value of X by using this relation. Then by multiplying this, you will be getting a particular load kVA or a particular fraction of full load kVA. At that particular fraction of full load kVA, these two losses will be one and the same, and the efficiency will be maximum. So from here I can write the output kVA corresponding to maximum efficiency as, the maximum efficiency is nu max. We will be generally representing the maximum efficiency as nu max. So output kVA corresponding to maximum efficiency as X times full load kVA, and for X you can make the substitution. So we will be getting it as square root of iron loss by full load copper loss into full load kVA will be giving you output kVA corresponding to maximum efficiency condition. You will get a more clearer idea about this while solving the problems associated with this. Let's see the first problem. The power rating of the kVA and voltage ratings are given. It's a single phase transformer. Iron and full load copper loss values are also given. You are asked to find efficiency at unity power factor on full load and half full load. So the total loss will be 350 plus 400 at rated full load condition. Okay. As this is the output power rating of the transformer in kVA, it's given very clearly that the load which is being connected is of unity power factor 1. So the full load output at unity power factor can be obtained by V2 I2 cos phi. The value of V2 I2 is given as 25 kVA. So you have to just multiply it with cos phi to get the value of power in watts. So you will be able to get the value of full load output power as 25 kilowatt. You know the value of total losses. So from these two terms you can easily find the value of efficiency. You have to just divide the output power by input power. Input power can be obtained by adding the output power with the total losses, and you will be getting the efficiency as 97%. See, it's very clear that the value of efficiency is very high comparing with that of the rotating machines, because the effect of friction and windage losses doesn't exist here. Next you are asked to find the efficiency at unity power factor on half full load condition. See, at half full load condition the value of copper losses will not be 400 watts. The value of copper loss at half full load condition will be half square into 400 watts. It's very clearly explained why it is taking a square here in the previous slides. You can refer there. So this copper loss value comes to be around 100 watts. The iron loss remains the same. Whatever be the load condition, the value of iron losses will be always a constant one. So in this particular case of half full load, the total losses will be actually 450 watts. And the half full load condition, at half full load condition, as the rated current is half, definitely the output power also will be half. So you will be able to get the output power as 12.5 kilowatt and the total losses as 450 watts. From here you will be able to obtain the efficiency as 96.52%. Let's see the next problem. In this problem, the voltage rating is given. The full load rated kV of the transformer is given. Its full load copper loss and core loss are also given. You are asked to find the kVA load corresponding to maximum efficiency and the value of maximum efficiency at unity power factor load. That's the first part. In the second part, you are asked to find the efficiency at half full load, 0.8 power factor leading. So in the first part, you are asked to find the power rating of the machine corresponds to maximum efficiency condition. That can be found out by using this relation. Please note a correction here. This is actually not 250, this is 150, and you will be able to get the value of the power rating corresponding to maximum efficiency as 160 kVA. As we all know that from the previous slides, at maximum efficiency condition, the value of copper loss will be same as that of the value of core loss. So at maximum efficiency condition, that is at this particular loading of the transformer, the value of copper loss is equal to the 1.4 kilowatt. Therefore, the total loss will be 1.4 plus 1.4, which is actually 2.8 kilowatt. You are asked to find the efficiency, that is the maximum efficiency at unity power factor. Now we know at maximum efficiency condition, the value of V2I2 is 160 kVA and cos phi 2's value is given as 1. So we can find the value of V2I2 cos phi 2 here as 160 kilowatt. So this is actually the output power and these are the losses. By using this output power and losses, we can find the value of maximum efficiency as 98.2%. Next, it is asked to find the efficiency at half full load, 0.8 power factor leading. So in order to find the efficiency at half full load, first you have to find the copper loss at half full load condition. The copper loss at full load condition is given as 1.6 kilowatt. At half full load can be found out by taking the x square into full load copper loss relation. We have seen this relation before. So we will be getting the copper loss at half full load as 0.4 kilowatt. As we mentioned before, the value of core loss at any load condition remains to be the constant one. So the value of core loss is 1.4 kilowatt and the value of copper loss at half full load is 0.4 kilowatt. Therefore, the total loss is 1.8 kilowatt. At half full load condition of 0.8 power factor leading, we will be able to obtain the value of V2I2 as 150 by 2, that is 75, and V2I2 cos phi 2 as 75 into 0.8, which we will be getting as 60 kilowatt. So now we know the output power at 0.8 power factor load, that is half full load, as 60 kilowatt, and the efficiency as output divided by input, which is actually 60 divided by 60 plus 1.8. You will be able to get the efficiency as 97%. In this problem also, you will be able to see the values of efficiencies are quite high because the machine which we are using here is transformer and does not consist of any friction and windage losses. We are going to study the concept of all-day efficiency in transformer and a numerical problem associated with this. This is a very important topic. The concept of all-day efficiency of transformer occurs in the case of distribution transformers. These distribution transformers are those transformers which you can see at the roadsides and in the substations. The loads which are being connected to this distribution transformers are we consumers. If you are considering throughout a day, the loading of this transformer will be varying continuously as we consumers will be using different loads at different instants of time or at different periods of time. So in this distribution transformer, even though its primary is continuously energized, the loads which are being connected to the secondary might be either full load condition for a particular period of time, and for the another period of time it might be 75% of the full load condition, and for another period of time it might be 60%. It keeps on varying. So the performance of such sort of transformers can be analyzed by using the concept of all-day efficiency. The relation for all-day efficiency is given here. It's output in kilowatt hour divided by input in kilowatt hour. This unit you might be quite familiar. You have studied them in your basic electrical engineering course. That is, the all-day efficiency is calculated on the basis of energy. This is a unit of energy. It is actually power into time. You will get a more understanding about this topic while solving the next problem associated with this. In this problem, you are asked to find the all-day efficiency of transformer. The power rated of the transformer is 500 kVA. This is actually the rated kVA, that is full load kVA of the transformer. Copper loss and iron loss values are also given. You are asked to find the all day efficiency. The loading pattern is given here. For 6 hours of the day, a day consists of total 24 hours. So for the first 6 hours, the loading is 400 kilowatt and it is loaded at 0.8 power factor. For the next 10 hours, this transformer is loaded with 300 kilowatts at a power factor of 0.75. Similarly, for the next 4 hours are also given here. For this 24 hours, the value of core loss will be remaining constant one. As we have mentioned before in the previous slides also, core loss is actually a constant loss. Based upon the loadings, the value of core loss also varies. At full load 500 kVA, the value of copper loss is 4.5 kilowatt. At 400 kilowatt loading, the value of kVA is 500 kVA. That means at this first 6 hours, the transformer is in full load condition. So definitely for the first 6 hours, the copper loss also will be 4.5 kilowatt. At 300 kilowatt condition, it is having a kVA value of 400 kVA. So it is not in full load condition. It is 4 by 5 times that of full load condition. So you have to find the copper loss corresponding to this condition. That is 4 by 5 the whole square into copper loss at full load. Similarly, at 100 kilowatt 0.8 power factor condition, you will be able to find the value of kVA as 125 kVA. See, this you can find out by using the relation V2I2 cos phi 2 divided by cos phi 2. That will be giving you the value of V2I2, that is the power rating in kVA. So like that you will be able to obtain the kVA corresponding to all this kilowatt values, from which you will be able to determine the value of copper loss at all those different loadings. Once all the copper losses during this different durations are calculated, we can easily find the value of total copper loss in this duration as multiplying each corresponding copper loss with the duration of time. That is, for the first 6 hours, the copper loss is same as that of the full load copper loss, which is 4.5 kilowatt. During the next 10 hours, the copper loss is 2.88 kilowatt. In the next 4 hours, it is 0.281 kilowatts, and in the last 4 hours, as there is no loading, means there will not occur any copper loss. So the total copper loss during this 24 hours is calculated in kilowatt hour here. This is actually the energy term. During this 24 hours, as I told before, the value of core loss set to be a constant one. So you can find the value of core loss in 24 hours by multiplying this 3.5 kilowatt into 24. So the total transformer loss will be the sum of this copper loss and core loss, which is said to be 140.924 kilowatt hour. Now we have to find the total output in 24 hours. In order to get the total output, you have to multiply this 400 watts into 6 hours plus 300 watts into 10 hours plus 100 into 4 hours. This will be giving you the total output in kilowatt hour. Once after identifying the total output in kilowatt hour and the total losses in kilowatt hour, you can easily obtain the value of total input in kilowatt hour by adding these two terms. So now you know the output energy in kilowatt and input energy in kilowatt. By dividing both of them for the 24 hours duration, we will be able to obtain the value of all day efficiency. Please note that the value of all day efficiency or the concept of all day efficiency is not the same as that of the ordinary efficiency term which we have studied before, that is efficiency is equal to output power divided by input power. No, it's not the same. In the case of distribution transformer, as the loading at the secondary side keeps on varying. In order to calculate its efficiency, this all-day efficiency concept has been introduced, and during determination of all-day efficiency, we will be using output in kilowatt hour and input in kilowatt hour, not output power in kilowatts and input power in kilowatts, just like how we have used in the case of a ordinary efficiency relation. With that, we are completing today's topic. All these topics are very important ones. Concepts and problems associated with today's topic has been asked regularly in the previous year university question papers. Thank you.